Here are solutions to homework set number 11 for ECE 376 Embedded Systems. This homework set looks at Z-transforms and digital filters, how to implement a filter in software. So problem 1 is actually a filter in the S-plane. Suppose x and y are related by a transfer function g of s. What's the differential equation relating x and y? Well, to do that, just multiply out the polynomials, cross multiply, and note that s means derivative. So this is the third derivative of y, second derivative, first derivative, y, derivative of x, x. So this differential equation is exactly the same as that transfer function. Interchange the two, same thing. The reason I use the transfer function is it makes analysis a whole lot easier. Suppose my input is a constant and a sine wave. Here I'll use superposition, treat that as two separate problems. When the input is a constant, x is 2, s is 4, dc. Here's the gain everywhere. What I care about is the gain of dc at s equals 0 times the input at s equals 0 gives you the output. Now repeat for the second term. Here s is j3, the input is 0 minus j4, real part's cosine, minus j is sine. The output is the gain at s equals j3 times the input at s equals j3 gives a complex number. Real part's cosine minus j is sine. The total answer is the sum of the two, your DC term plus the AC term. So that's in the S-plane. Suppose instead I'm in the Z-plane. In the Z-plane, Z means next value, so multiply out the polynomials, cross multiply. This means y 2 samples in the future, next value of y, current value of y, next value of x, current value of x. So this difference equation is the same thing as that transfer function, just different way of writing it. Where the transfer function is nice, that makes analysis easy for sine waves. If the input is a constant and a sine wave, treat that as two separate problems. At DC, s is 0, z is e to the st, that's conversion from s to z-plane, or 1. To find the output, I find the gain at the frequency of the input times the input gives 1,000. For the second part, s is j omega, z is e to the st, or a complex number, x is 0 minus j3. Analyze. This is the gain everywhere. What's the gain at my input frequency times the input at that frequency gives the output at that frequency. Again, what that means is real part's cosine minus j is sine. Put the two together. The total answer is your DC term plus your AC term. Problem 3. Suppose I have a filter like this in the S-plane. Come up with a discrete time compensator that has the same gain versus frequency. Now, the approach I like is map the S-plane to the Z-plane as e to the st. If I have a pole at minus 3 in the S-plane, it's 0.9704 Z-plane. Minus 7 S-plane is 0.9324 at Z-plane. Minus 20 S-plane, 0.8187 Z-plane. So 3 poles in the S-plane, 3 poles in the Z-plane, and the map is e to the st. Add a gain k to match the gain somewhere, typically DC. The DC gain should be 2.38. Pick k so that g of z also has a gain of 2.38. Solving, I get k is 0.0008. And here's g of z. If I want to check, plot the gain versus frequency for g of s. Also plot the gain versus frequency for g of z. Here s goes to j omega, z is e to the st. Plot the two together, and the blue line is g of s, the red line is g of z, and see they hit so close to each other, it's basically the same filter. What that means is when I implement this filter, it really doesn't matter if I implement it in the S-plane using an op-amp circuit with capacitors, or in the Z-plane with a program. The end user really can't tell the difference. Problem 4. This also works with complex poles. If I have a 0 at the origin and 2 complex poles in the S-plane, in the Z-plane, once again, I map is e to the st. I should have a 0 at plus 1 in the Z-plane, a pole at 0.95 plus minus j.19 in the Z-plane. So this filter in the S-plane looks like that in the Z-plane. This assumes a sampling rate of 0.01. Change the sampling rate, I change the pole location. Pick K to match the gain. Here I can't use DC because at DC the gain is 0, and I have 0 is K times 0, solve for K. Pick something other than 0. I'm going to pick 20 radians per second, roughly the resonance in the S-plane. At 20 radians per second, the gain should be 0.99. Pick K so that the gain is also 0.99 in the Z-plane. That gives you K is 0.05, so here's G of Z. Or equivalently, multiply out the polynomial, either one. To check your answer, plot the gain versus frequency for G of S, plot the gain versus frequency for G of Z, plot the two together, and the blue curve is G of S, the red curve is G of Z. You can kind of see that they're basically the same. So once again, it doesn't matter which one you implement, G of S or G of Z, it's the same filter. G of S I would implement with an op-amp circuit, G of Z I would implement in code. To illustrate that, the code, if this is your G of Z, I would implement it as follows. I have Y is your gain times the input, cross multiply, solve for the highest power of Y, convert back to time, and this is non-causal. I have the future value of Y, do a change in variable or shift time by 2, and here's the same difference equation, just using old data. That's basically my program. I've got to remember the current input 1 sample ago, 2 samples ago. I need to remember the output 1 sample ago, 2 samples ago, and the current output is 1.92 times the previous output, minus 0.94, output 2 samples ago, plus 0.05 times the current input, minus the input 1 sample ago. Do that every 10 milliseconds, and I've implemented G of S. So this is kind of the point behind Z-transforms. If you ever want to implement a filter in software, the proper way to do it is convert to the Z-plane and then implement that filter in the Z-plane. Advantage of filters in the Z-plane is I can implement that exactly. So there's no approximation here. This filter is exact. But to do that, I need to go from the S-plane to the Z-plane. That's actually not too bad either. Just do a mapping. If I have n poles in the S-plane, if I have n poles in the Z-plane, everything maps as e to the st. And that's homework set number 11 for ECE 376.